Hi everyone, welcome to the third series of the dynamic programming number of possible way. The third example is called unique path. This question is from LeetCode. If you want to check it on LeetCode, check for the title called unique path. So the question is we are having a grid of m times n, and then we always start from the top left corner, and our goal is always at the bottom right corner. And the other key point is we only able to move either down or right at any point in time. So here this is a dynamic programming kind of question. There are two approaches, as I explained before, with a bottom up or a top down. So if we are trying, it depends on how you see the problem. You might find it easier to figure out the bottoms up approach, and sometimes it's the top down approach is much easier to be figured out. So here let's see how we did it in the bottoms up approach. For this example here, it's 3 times 7, right? The m is 3 and the n is 7, so we will have a grid of 7. So for the base case, we know that basically the start, we have one way to reach the start, that's not moving at all. And then to get the how many way to reach this point here. If we are starting from the top left, then we only have one way to go, right? So this is also only one way to reach this part to the right, and only one way as well to reach the bottom, right? And here comes when we want to reach the other part, the index, the position 1.1, and there is one way to reach from moving right and then moving bottom, or moving bottom then moving right. So there is two ways to do it here, and you will realize soon that to move on the first row, we basically only able to move left, so all of it will have 1 as its position. And same thing, if we try to move to bottom, there is only one way to do it as well. But when we are trying to reach the 1.1, for example, we can either reach it from the top or the left. So there is two way. And here is the same thing. There is two way to reach 1.1. So to reach the 2.1, there is two way from the top, and there is one way from the left. So there is 3 here, and basically we just adding up top and the left. So we will soon able to solve everything here. So 6 and 10 and then 15 and then 21 and then 28, and here's what we are interested in the bottoms up approach. And same thing, when we are trying to do a top down approach, we are trying to solve the problem from here. It might be a bit harder to show it in a table, but what we basically think of is if we have a function of m comma n, right? How do we know what is the result of m comma n? Then basically we know the formula is how many ways to reach 1 on the left and how many ways to reach 1 on the top of it, and those two number of way being accumulated, and it's become the m times m comma n. So the formula becomes f of m minus 1 comma n plus f of m n minus 1. So this is the initial the recursion condition here, and we also have extra condition, which is saying f of 1 comma 1 is equals to 1. it depends on if we say the position is m comma n as our goal, then our initial position is 1 comma 1. Yeah, so there's one way to do it. So this is the base case here, and for f of anything less than 0, like m less than 0 comma any n, it will be 0, and f of any m, but if the n is smaller than 0, it's also 0. So here it's saying like if the top is out of bound, it will be 0, or if the left is out of bound, then it will be 0 as well as the base case. To make it clear how to code it, I also recorded my live coding, so I will play it and give a commentary there. So here what I'm trying to do is I'm doing the bottoms up approach. I'm creating an array of size m times n, initialize the position 0, 0 to equals to 1, and then we try to do a for loop to the entire DP. First thing is we want to skip out the I equals 0 and j equals 0. So we continue because we already have the initial value there. Here, then we try to get the DP of the top, but it might goes out of bounds if we are in the first row. So we try to do it for the DP I minus 1 j if the I is larger than 0, and same thing for the column if it's on the left and if it's still in the bounds, or otherwise we have a 0. And then DP of ij will equals to the top, a number of way on the top, and the number of way on the left. And then basically we return the DP of m minus 1 n minus 1 as the number of way at the goal itself. So here I'm trying to do it with a top-down approach. First, we will initialize the recursion of signature m's n, and then basically when the n is out of bounds or the m is out of bounds, we want to return a 0 in that case, because out of bounds means there is no way to reach it. And when the n is equals 1 and m is equals to 1, we have one way to reach it. Note that here my assumption is m and n is based on 1 instead of 0 based, and our output means we try to solve it in a recursion way. Solve m minus 1 and comma n, or and plus it with the solve m comma n minus 1 as the result, and we try to call, so we try to solve it from the goal of m comma n, and then see the output from the subproblem to add it together. And the next thing is we try to add a cache here. This case is for reducing, like the subproblem we have solved before, we not try to calculate it again and again. So here is the string key for the DP. So each subproblem have its own unique key to make sure if it's something that we already solved before, we try to return the result instead of doing the recursion again. And when we are first time doing the recursion, then we put the result to the cache. Here I should put the output itself. Try to run it, and yeah, it should success in that case. Yeah, so that's it for this video. Thanks for watching, and see you on the next episode.